This is ATP synthase, the electric motor of the cell. Yet even this remarkable machine is small compared to the bacterial flagellar motor, a massive high-torque rotary engine built on the nanoscale. It can spin hundreds of times per second, push a long helical tail like a propeller, and drive a bacterium through its environment with astonishing power. It is one of the most impressive molecular motors known. The flagellar motor is composed of several ring-shaped structures, such as the LP ring, which helps stabilize the spinning assembly, and a C ring inside the cell that functions like the motor's control wheel. Each ring plays a distinct mechanical role, ensuring the entire engine stays aligned while it spins at extraordinary speeds. Running through the center is a drive shaft, or central rod, that connects the engine to the long flagellar filament on the outside. The motor is powered by 11 stator units that sit alongside the rotor. These are not passive parts. They are miniature rotary engines themselves, each capable of generating torque as protons flow through them. The cell can recruit more or fewer stators depending on how much power it needs. More stators mean higher torque, while fewer help conserve energy. When the motor requires maximum torque, it also recruits an additional regulatory protein, which further stabilizes the stator units. As more stators lock in, the entire assembly becomes sturdier, ready to deliver bursts of power at astonishing speeds. This dynamic tuning system gives the bacterium remarkable control, allowing it to respond instantly to changes in its environment. In a way, it's like the cell is upgrading its engine on the fly, boosting performance only when the journey demands it. The whole system works like a collection of interconnected gears. The C-ring behaves like a large gear, and the stator units act as smaller power modules that latch on and drive it. Together, they create a remarkably efficient nanoscale engine. Even more astonishing, the motor can switch rotational direction on demand with extraordinary efficiency. A key regulator of this behavior is a switch protein called CHE. When CHE binds to the C-ring, the stators engage from the inside, driving the motor in one direction. When CHE is released, the motor effectively changes gear. The stators shift to the outer edge of the ring, reversing the direction of rotation. This elegant mechanism allows the bacterium to toggle rapidly between clockwise and counterclockwise spinning. CHE itself is guided by the cell's sensory system, proteins that help the bacterium detect what's around it and decide how to move. When these signals tell the cell to change direction, CHE steps in and adjusts the motor's rotation, steering the bacterium toward better conditions. When you step back and look at it all together, the flagellar motor is astonishing. A self-assembling, self-tuning engine that can speed up, slow down, and even reverse direction in an instant. And all of this happens inside a single bacterium, built atom by atom through the cell's own molecular machinery. It's a reminder that some of the most remarkable machines in the universe, both elegant and intricately regulated, operating with almost unimaginable complexity, aren't made in factories. They're crafted by life itself on the nanometer scale. This is iJEP Studio. I make structural biology animations. If you like my content, please subscribe. Thank you for watching.